this is very important chapter. It's very important for two reasons. Well, that's the chapter that sent me to grad school. Remember, I went to the professor after the class and I told him I understand the math, but I didn't understand the physics, why this is happening. And he told me, well, after you graduate, come to grad school, you will get it. I'm not going to tell you this today. I'm going to tell you, no, we will get it in chapter 6 and 7. There are weird things that will happen today. All right? And the answer to those weird things will be in chapter 6 and 7. Right? But the second reason why this is very important, behind showing the huge difference between subsonic and supersonic, is that this chapter is really the building block for the rest of the course. So a lot of students every year, they have very hard time later in chapter 4 and 6 and 7, we are going to skip 5. So in 4, 6 and 7 and even 9 and 10, they will have hard time because they didn't get today class. Right? So they go to chapter 8 and 7 and 5, set 4, 5, 4, 6, 7, 8, 9 and 10 too, and they still have questions related to this chapter. So today in the break you have to get a lot of coffee, okay, so that you can really don't miss anything during today's lecture. Right? And ask me a lot if there's anything that's weird, ask me. Right? Okay, so we are going to answer those kind of questions, like basically here's a rocket engine, those are the end of the Apollo rockets, Saturn rockets, the Apollo mission basically, and you can see how the exit, the nozzle, is getting bigger and bigger and bigger. It gets smaller first and then get bigger later. So the middle part, the part when it gets like really tiny, that's the throat of the engine. So those engines are, if I draw them, they will be like this and then like this, right? Or actually even like this. They expand a lot. So we will get today why the area exit is much bigger than the throat area, and we will calculate too how large it is. Right? As a matter of fact, today if you look at this area and you compare it to here, you know what is the velocity leaving this guy just from the area issue. You'll be able to tell what velocity is leaving. Right? So compressible flow change, change meaning his Mach number, pressure, temperature, density, change for any change due to any change in the area or any change in because of the friction on the pipe or because of heat transfer. Those are the three things that we're going to deal with in this course. Change due to the area, change due to friction, change due to heat transfer. Right? Having the three of them together is really a little bit complicated. We'll do this at the end and with the help of a computer. But to be able to do it by hand, we will have to split those things. We will just basically have to say, let's just get the change due to the area. If I make the area twice as big, what will happen to my Mach number, pressure, temperature, density? And then later in chapter 9 we will say, well, what if I have no area change, the same cross-section area, but just a lot of friction? What will happen? And in chapter 10 we will basically say, well, what will happen if we just no friction, no area change, but we have a lot of heat transfer? We are cooling the duct or we are heating it by the sun or by whatever. What will happen to the flow? And then at the end we will say, well, now what happens if we combine the three of them together? What would happen to the compressible flow? So in this chapter, this is kind of the start. So we'll just have the area change. We'll kill the friction. No friction. How is that possible? Isentropic. Assuming isentropic flow. No friction on the wall. And no heat transfer. Well, that's also implied in isentropic. So isentropic means it's adiabatic and reversible. So that's what isentropic stands for. Adiabatic plus reversible. Alright? So is that really practical? Can you treat with something like this as isentropic flow? No friction, no heat transfer? Well, if the area change is so big that it's really the dominant force affecting the flow, you could get a really very close numbers by neglecting the other two. By focusing on the beef. Where is the beef in the problem? You can get not super accurate results. I'm not saying let's design this nozzle based on our isentropic calculation. But what I'm saying is that it's a very good starting point for the calculation to just neglect the smaller effect and focus on the big change. Right? So if I have a constant area duct between here and Dallas, can I just neglect the friction? No, that's the dominant thing. How could I neglect the friction in something like this? All right? But if the distance is short and the area change is huge, maybe you can get away with actually just focusing on the area. Right? So that's what we're going to do. So the problems would be like this, that you will be given the initial condition, the pressure, density, velocity, enthalpy. When I say enthalpy, I mean also the temperature. Because for ideal gas, H is CBT. So basically the enthalpy and the T, they are almost the two sides of the same coin. Okay? And what are our job? Our job is that if we know the area change, if we know basically what's the final area, what's the throat area, what's the initial area, we will be able to get those guys. We will know what is the new pressure, what's the new density, what's the new velocity. And when I say, this is important, when I say plus dP, doesn't necessarily mean what? Yeah, right. It doesn't mean that the pressure will have to increase. I'm just saying plus a change in the pressure. So that dP and that d rho and that dV could be plus or minus. As a matter of fact, the first thing that we will do right now, that was the thing that really struck me as amazing when I was undergrad. We will just get the sign of the dV, not the magnitude, but the sign. Will the dV plus or minus? So will the dV increase or decrease? Okay? And we will find out that that sign will depend on the Mach number. So subsonic flow will do something, supersonic flow will do something else. One of them will make dV plus, the other one will make dV minus. Okay? So now how am I gonna do this? How am I gonna get the pressure and the velocity and the temperature at the end? What's my tool set? What do I have to be able to calculate those guys? Continuity, momentum, and energy equation. So every single chapter, I'm going to ask you the same question. And every single chapter, you're going to tell me, well, let's write the continuity, momentum, and energy equation. We will do this for everything. And we will solve them together, or the book will solve them for us. And we will get the solution as an equation that we can use. And even they will put it in the table at the end of the book for us, so that even if you don't want to substitute in the equation, you can just use the table too. All right? So let's see what are the equation that we can use. So here is a section where the area basically jumped from A to A plus dA. All right? So I got area over here, and I got A plus dA over here. And again, plus dA doesn't necessarily mean that the area will increase. This analysis will work if you increase the area or decrease the area. All right? It just, there is a change in the area. As a result, the pressure P become P plus dP. And the velocity V become V plus dV, and the density become rho plus d rho. All right? Start with the first equation, continuity equation. What's our assumption? Steady state. Yeah, so all those things are supposed to run at steady state, you know. The flow coming in need to be equal exactly to the flow leaving at the end of the engine. Otherwise, the nozzle will explode, basically, right? So steady state works. And isentropic, we said it's too much to handle the heat transfer and friction at the moment. And neglect the change in the potential energy. Well, first of all, let's assume it's horizontal. But even if it's vertical and this thing is a rocket flying up, it's pretty good assumption to basically neglect the potential energy, because the change in the velocity and the change in the enthalpy is just too much compared to the, how many? Compared to the, what, 10 meters difference? It's nothing. Those 10 meters of air, especially if of air, not of water. So potential energy, when it comes to the water, it's a big deal to neglect 1 meter of water, for example. But it's very easy to neglect 10 meters of air in the energy equation, especially when there is a huge change in kinetic energy and pressure. Alright, so first continuity equation, steady state, m dot n equal m dot out. What's m dot n? Rho AV, rho AV. What's m dot out? The new density, the new velocity, the new area. Rho plus d, rho v plus dv, a plus dA. Alright? So you multiply those things, you get those terms. Right? A lot of terms because there are basically just 3 brackets. Rho AV, d rho, dv, d rho, and let's call this a third order term. First order which have dv and dA and d rho, and second order term which is have. So I'm neglecting the second order term and third order term. Why I'm doing this? Imagine, not really imagine, it's basically we are taking the limit as those guys go to 0. So this calculation is not for A is here and A plus dA at the end of the rocket. No, this is supposed to be a continuous solution. So we are doing it basically every millimeter, every micrometer. We are doing it every small distance. Here is the new area. How much is the new area? Well, we increased 1 millimeter square. Good for you. Let's do the calculation. We are doing it really at very small distance, all right? So you should imagine that this is just a very small change, and therefore I can take the limit as dA, dV, and d rho go to 0. When you do this, you'll find out that this term will dominate compared to this and this. Why? Just divide the whole thing over d rho, dV, dA. This will end up being 1. This will be rho A divided by dA, d rho, and this guy will just become rho over d rho. And then when you take the limit, this guy will shoot to infinity, while this guy will just be 1, and this guy will be, I don't know, 100, 1,000. So at the limit, those will disappear, and those the only one will survive. At the end of the day, those 3 terms, you will have them. They will be like this, and that's the continuity equation. Good. Second equation, momentum equation. So to write the momentum equation, we need 1. What do I need to write the momentum equation? Huh? I need to define what's my control volume. Here is my control volume. Second, I would like to point out where is the positive direction. Third, I would like to put the forces, so I can say that the forces are equal to the change in momentum m dot out, v out minus m dot n, v n. So here is the plus, here is the forces. What are the forces? P, A in this way, P plus dP multiplied by A plus dA in this direction. Alright? Any more forces? I got the pressure here. It's this guy. And I got the pressure here multiplied by the area here. What else? Any other forces? Anything else? Friction or something on the wall? Huh?
Or constrain this.
No friction, right? There is no friction. So what else is there?
Pressure.
Pressure in the middle. Right. So look at this. This surface also has pressure force on it, right? What is that? That's the cone. That's the conical wall area. This is a nozzle expanding. It's axisymmetric. So that surface has pressure on it. Which direction the pressure should be? We always said the pressure should be normal to the area. Excellent. So we should have put the pressure like this. Multiply, so it's that pressure here multiplied by this area. What is that pressure here? If I have P here and P plus dB over here, this must be B plus over 2. How did you linearize this? Who told you it's linear? Well, it's very infinitesimal change. So yeah, I can assume linear. Alright, and what is that area? I don't know. But, you know, we'll have to calculate. It's not dA, right? This area is not dA. What's dA? When we said this is A and this is A plus dA, what is that dA exactly?
Infinitely small.
No, but what it is? What is it? Huh? I can't hear you.
Marginal change in your.
But in the drawing, what is ADA exactly? It's the projected,
Cross-section.
different cross section. It's basically between the smaller inlet area and the bigger area, right? Right? It's basically, if I draw them like this would be the TA. I'm making it bigger, of course, so that you can see, but this is basically the DA, where the smaller circle is the area and the bigger circle is A plus DA. Right? Cross-section area, the big one is A plus DA, the smaller is A. The difference between them is the DA. Okay, so that pressure force normal to this area, I'm writing the X momentum equation. Which force I need? I need only the horizontal component, right? The horizontal component of that force is the one contributing to my X momentum equation. The vertical component kind of eat each other, basically, cancel. I need the horizontal component, alright? So after I calculate this area, which is not dA, that whole area is not dA, I need to take cosine, cosine this angle. So here's a very cool trick that you should have remembered from fluid 1. And that is, this horizontal component of the pressure force is equal to the whole pressure force, the whole pressure, not cosine of it. The pressure multiplied by the projected area in that direction, or basically the dE. You get it? So that's why this force, P plus dB over 2 multiplied by dA, that is the horizontal component of the pressure on the wall. So rather than saying the whole pressure multiplied by this area and then take cosine this angle, remember from hydrostatic in fluid 1, when you had those gates, the curved gates, and we wanted to calculate what's the V horizontal and what's V vertical. The V horizontal was, let's multiply the pressure on the gate times the projected area. That's what we are doing over here. Anyway, that's this guy. Alright? So here are the forces. Plus PA plus P plus dB over 2dA minus P plus dBA multiplied by unsteady term that should go to 0 because it's steady state, plus m dot out V out minus m dot in Vn. Of course, m dot out and m dot in, they are the same, and they are simply rho EV from the continuity. It has to be steady state. So even the m dot out and the new velocity and new area and the new density, at the end of the day, it has to be also rho EV. So you just have m dot multiplied by V dot out minus V dot in. Here it has V, here it has V plus dV. So the difference between them is dV. That's the momentum equation. You cancel B with B and the second order term will go to 0. So the dB, dA go to 0. The same trick we did before, taking the limit. This will end up being the momentum equation. So you got the continuity equation. Ouch. And you got the momentum equation. Alright? So he's basically saying let's put them together. So we'll take this dV out from the momentum equation. Sorry, from the continuity equation. And instead we will write basically dA over A and d rho over rho, and there's an extra V here. We are almost there. Magic will happen right now. So this is just combining continuity and momentum equation together. Alright? What are we trying to do? I mean, those are the tools in our hand, but then, okay, we wrote them. What are you trying to do? We are trying to solve this thing. Okay, I am just trying to find out what will happen here. I'm trying to find out what is the new dV. Will the flow increase its speed or decrease its speed? Alright? So, and what's my input? My input is the dA. So it's kind of dA is given, and dV and d rho and dP and dm, those are the unknowns. Okay? So out of those two equations, if we only can get the area on one side and the pressure on the other side, the area on one side and the velocity on the other side, That's what we want. That will help us to understand that if the area increased by 1%, the pressure will increase by 1% or decrease by 1%. All right, so we are almost there, except that, you know, dB and d rho together doesn't work. I don't want two unknown in the same equation. I just want pressure and area, input, output. So how can I get d rho out of this equation? Well, remembering the chapter 2, the acoustic speed was A square was partial V partial rho at constant S, isentropic basically. Well, the whole flow is isentropic. I can just use this equation. I'm assuming isentropic flow. Alright? So basically, from this, you can say dB is A squared d rho. So you can get this d rho out, and you're almost here. Now you have dB, and you have the area. Alright? Rearranging it, just putting dA on one side, and let's put all the dB on the other side, you'll end up with this. dB 1 minus rho V square over rho A square equal rho V square dA over A. Alright? Rho cancel with the rho, V square over A square, that is, what's V over A? M square. And this is the equation we have been hoping to get. Input is dA, output is dP. Alright? Mach number and V square, those are the stuff at the input. This is what you started with. And now this equation tells you basically what will happen to the dB as function of dA. Alright, so now what's interesting is looking at the sign. Okay? So to get that sign, you just do one more extra step. So rho V square, you can prove that it's gamma M square B. Why? Here is the proof. It's just two steps. Well, the M is V over A, and then the A is gamma RT, and then you can cancel gamma with the gamma, and you realize that B over RT is rho. So V square over rho is basically gamma M square over P. Okay? So now the equation, after you take rho V square and write basically gamma M square P, you will end up with dB over dA is gamma M square 1 minus M square B over A. And along the same procedure, you can end up with also another equation for the velocity. dV by dA is 1 over M square minus 1 V over A. And now let's look at those two equations. And the question we want to answer is dB by dA plus or minus? dB by dA, that's the rate of change of pressure with the change of the area. So if dB by dA is plus, what does this mean? It means that the bigger the area, the bigger the pressure. And over here, dV by dA, the same thing. dV by dA, that's the change of V with respect to A. So if A increased by 10%, will the V also increase by 10%, or it will be negative? So we are interested in the sign of this. The sign of dV by dA. Is it plus or minus? Bob is saying minus. Anyone saying plus? dV, let's look at dV by dA.
It should be plus if it's going to be if you want it to go supersonic, it needs to increase.
I'm just asking dV by dA. Is it plus or minus?
It can be either way.
Excellent. Sean is saying dV by dA can be plus or minus depending on why it can go every way. Can you explain? Why it can be plus or minus? Because see, V is plus all the time. That's the magnitude of the velocity coming in. The area is always plus. So what would make dV by dA plus or minus? The M square minus 1. It's that bracket that holds the sign. The M square minus 1 can be plus or minus. How it could be plus for M square equal 2, 4, 8, anything more than 1. It would be plus. And M square minus 1 can be negative if M is less than 1. So anything that's flying with Mach number less than 1, any pipeline with Mach number smaller than 1, this would be negative. So hence that change. So the mass basically tell us that depending on that magnitude of M, if M is bigger than 1 or less than 1, this will flip the sign, dV by dA. So a supersonic flow will go to something like this, and he say, wow, area is getting bigger, I better what? Increase. And supersonic flow will love it. That's why they build the rocket nozzle with something like this. They give him more and more area so that his velocity get bigger and bigger. And subsonic flow will go to see something like this, and he will say, that's a diffuser, I better slow down. Same geometry, different physics depending on that magic number. So I have 3 questions. So first, Jason had his hand raised up, and then Yang later. Huh?
Yeah, do you have to, when you put in 1, it's, that's defined.
We'll talk about 1 in a second. So very interesting, right? What happened when m equal 1? Very interesting to actually answer that question. I will answer that in a second. And Yang, you had a question. Same question? Someone else had a question. John, did you have a question? Anyone? Right. So this basically what blew up my mind. So the lecture, when I was undergrad, lecture finished here. Okay, and the professor said, okay, we'll see you next week. And so like, what? How we can see me next week? I want to understand what happened. And he said, well, you don't understand how we came up with I told him, yeah, I understand the derivation. Everything makes perfect sense, but what's going on? Why the slope is plus or minus depending on the Mach number? How you can give him more area and he still speed up? So let's.
You asking?
No, I was asking him at that time, right? So the answer. We will answer right now basically, again, how is that possible? And then why exactly this is happening, that would be the chapter 7 and 8. 6, 7, and 8. But for now, let's answer Jason's question first. What happened when m equal 1? Alright? At this point, what will happen? So let's just remind ourselves that coming from fluid 1, subsonic flow, we dealt only with subsonic flow, things that are slower than the speed of sound. And you guys after chapter 2, you understand what's the big deal of flying subsonic or supersonic. It's flying knowing what's ahead of you, or flying basically with your hand behind you, and you hit the wall first and then, it's a wall. That's flying supersonically. You don't see the nozzle in front of you when you are flying supersonically. You don't feel it, okay? You just go blindly into it. So from fluid 1, we basically know this, that you give me smaller area and I will slow down or speed up. Speed up because I want to keep my m dot the same, or basically because my density didn't change that much. Keeping my m dot the same because that's the conservation of mass. There is nothing called conservation of volume, really. It's conservation of mass. We want to keep our mass the same. But because the density of liquids and gases that are flying at very small speed, their density does not change that much, immediately the conservation of mass between here and here translate automatically to conservation of volume too, volumetric conservation. VA equal VA. And so immediately, area getting smaller, V need to get bigger. M smaller than 1, and you are giving him more area, well, you have to basically speed up. So subsonic flow speed up here and slow down there, just to make AV equal AV. Alright, that's what we know. And this rule apply all the way up to Mach 1. Okay, any subsonic flow basically work according to this rule. Give him more area, he will speed up to maintain the same mass flow rate. Give him less area, give him more area, and he will slow down. Okay. And supersonic flow, we just established that it's completely the opposite. So this, for a supersonic flow, that's a diffuser. He will slow down, his pressure will build up. And this, for him, that's a nozzle. He will speed up and his pressure will drop. And something like this. Right? So now how is that possible? How could you do this? Because it's the density. So here I'm marking the density as basically density drop, not just change, the density drop in this geometry for a supersonic flow, the density drops so much. Density drops so much to the extent that all that increase in the area is not good enough. So to maintain the same m dot, and m dot need to be the same, there is no violation of the conservation of mass. The velocity basically just shoot up to basically keep up with the drop in the density. Now the question that you should ask me is,
Why increase the area so much if you want maximum volume for
no, that's not the question. The question that you should ask me is,
Why does the density change so much?
exactly, why does the density drop so much? Why? What happened when the area is getting bigger? And for that, you go to grad school too. No. For that, you wait for chapter 6 and 7. You will get it. I will explain it later at that point. But that area make the supersonic flow density drop so much that the velocity need to pick up to keep the balance. Hence, he accelerates. Right? Now, Jason question, what happened, before I answer, actually, let's just say, what happened when m equals 0? M equals 0 is not because V equals 0 and there is no fluid mechanics, and that's the trivial solution. No. M equals 0 because, how could M equal 0? It's not because V equals 0. It's because,
It's vacuum.
Yeah.
no, it's because M equals 0 because, not really 0, almost 0, like really, really small. Like, huh?
A is really big.
No, it's not the area, it's the,
No, the A, the little symbol A.
excellent. Tommy is saying basically it's the acoustic speed is so big. How it would be so big? Why A would be so big? Almost solid like, almost incompressible. Almost, so basically when M goes to 0, that's incompressible flow. So the incompressible flow, all this analysis in fluid 1 was the limit when M go to 0. So all the solution that we have will turn into basically the equation in fluid 1 when M goes to 0. Right? So incompressible flow is the limit for basically very large acoustic speed, or basically almost incompressible flow. Alright? Now, so that's easy to answer, right? Now what happened when M equal 1? So 1 over 0, what will happen? So this will, so first M equals 0, that's the limit of incompressible flow. M equal 1, that make dA over A equal 0. How could dA over A become 0? That means that it's either minimum or maximum. Well, it happened to be minimum. Alright? So mathematically this corresponds to a minimum or maximum area. So then Mach equal 1 will only happen at the minimum area, the throat area. So the only way to go from subsonic to supersonic is to build a conversion diversion nozzle. Or to go basically, if you want to go smoothly from supersonic to subsonic, they basically the area M equal 1 will happen at the throat. Right? This, you can do this rough, like really with a shock wave too, but let's focus on this one. So if you have a tank with almost 0 velocity and you want to turn that into supersonic flow in your lab or at the end of the nozzle, the rocket nozzle, the way to design this is basically to go to a minimum and then max. So this question was not that easy to answer actually. So a lot of people, you know, in steam engine, steam gas turbine, they would have the high pressure and the high temperature steam building in the boiler, and then they want to send this through a nozzle so that they can hit a wheel or a turbine basically with that very high speed steam, so that turbine can turn something, right? Can turn the jet engine, the propeller in front of the turboprop, can turn the generator in a gas turbine, right? A steam power plant. So they basically kept, before this guy, people kept basically building nozzles like this. And they would say, but maybe if we make like this huge area, maybe it will do it now. You know, maybe if we, you know, just a tiny. They kept trying to shrink more and more, but they never get more than Mach 1. They didn't know what Mach at that point, Mach 1, but the point is, they couldn't really achieve velocity higher than the speed of sound. Right? And so this guy actually, he actually was a mechanical engineer, and his boss fired him because he didn't like his design. And he ended up being very famous, not because of this nozzle. I mean, he's famous for us because of the inventing the converged divergent nozzle, but he made a lot of money by inventing a cream separator. It's a separator that separates the cream from the milk, and he sold a lot of them. But then he invented that nozzle, and he came actually to Chicago. There was a world exhibition at that point, and he basically showed that design. And so that's when he was younger, and that's when he was older. De Lavelle. And basically his nozzle was a convergent divergent nozzle. And so suddenly when he made this design, now he could achieve velocity that have never been achieved before him. And that thing could fly basically much, much faster than any pairing they can take, because it's just basically spinning like crazy. And that's basically his design. See, this is the wheel. This is the steam will come in here and will leave from this. So when the steam, it's basically when I hit you with the pin and bounce back from your head, right? That's, ouch. That's basically how you get double the momentum, basically. So the steam kind of come here and go this way. So this thing will spin like really quickly. And here is the steam will come from here, right? And you can see how is the nozzle is designed, right? This part is the conversion part. And then you can see here the throat. And then basically the area get bigger. All right? And he got 4 of them basically to hit different places of the wheel. But basically that's his invention. All right? So it took people more years to actually take a picture of that flow and see that it's actually supersonic inside the divergent part, right? But he was the first one to actually came up with that design.